Hello, and thank you for choosing to join this More Than Maps workshop. The More Than Maps workshop series comprises 5 workshops, which you can work through consecutively, in any other order, or just choose the workshop that you think will benefit you the most and ignore the others. You can do as many or as few as you choose. However, the workshop series as a whole aims to improve your understanding of the types of research skills, practices, frameworks and methods that we use as researchers to study our changing coasts, and specifically to study coastal adaptation. You can choose from workshops that provide an overview to the research disciplines that we use to research the coast, Workshop 1, to learn how to use Google Earth Engine and JavaScript for environmental mapping, Workshop 2, or how to apply a stakeholder analysis to better understand people who are at the heart of environmental problems and challenges, Workshop 3. Or you can study a case study of Somerset levels and flooding at Somerset levels to better understand how we can use mapping and remote sensing data to study flood risk, Workshop 4. Finally, you can find out about frameworks and methods to study how households can adapt to coastal hazards, Workshop 5. We're extremely grateful for all the different funders, partners and organisations who've supported this workshop series to date, and you can see these types of organisations on screen now. I hope you enjoy the workshops or workshop that you choose to participate in. Welcome to Workshop 2, using Google Earth Engine for environmental mapping. This workshop was developed by Ms. Jana Fidai, and she's very much looking forward to sharing her expertise and knowledge on Google Earth Engine, JavaScript, and environmental mapping. Don't forget to open your workshop booklet to support this workshop and enable you to take part in all the interactive elements. I hope you enjoy Workshop 2. We are always looking to improve the More Than Maps workshops and learn from you how we can make the experience better and improve your learning about coastal change, climate change and coastal adaptation. Please take 1 minute to complete this survey to help us improve the workshops.
Hello and welcome to More Than Maps Introduction to Google Earth Engine. So today's session is just going to be some slides followed by some guided work with Google Earth Engine. So the idea of this workshop is for you to learn a bit about sargassum blooms and use it as a case study for climate change adaptation and hazard mitigation, but also to understand some remote sensing theory, how it can be used to monitor environmental change, and also to navigate the Google Earth Engine platform, which we'll learn all about in a minute, but it's a free open source online website-based platform where you can use remote sensing data and apply different algorithms, methods, things like that, and create outputs which are really useful. So in order to do that, you need to be able to use JavaScript. So we'll have a bit of an introduction to JavaScript as well. So what is a natural hazard? A natural hazard can be defined as any natural process or phenomenon that may cause loss of life, injury or other health impacts, property damage, loss of livelihoods and services, social and economic disruption or environmental damage. So that definition is taken from the UN, and when we think about a natural hazard in this context, we often jump to really big events. For example, flooding, which can cause all of those things, loss of livelihoods, it can damage homes, buildings, it can also cause the loss of life, and pretty much ticks all those boxes. Similarly with earthquakes and volcanoes, these too can also have these impacts. What we don't often think about are often sort of what we can consider smaller events or more environmental events that can also be considered natural hazards. So An example of one of these smaller events, environmental events, is sargassum blooms. So just to give you a bit of background information about sargassum, so you know what I'm talking about. So sargassum is a type of brown seaweed. There's over 300 different species of sargassum found globally, but there's two that I'm mostly interested in and that we're going to talk about today, and they are sargassum natans and sargassum fluitans. And these two species are what we call holopelagic, which means that they are always floating. They never grow roots or hold fast, and they never grow in seabeds. They're always floating on the surface of the water. So you can see in the bottom image there that it's just floating on top of the ocean, and in the top image you can see sort of like a zoomed in version where you can see they've got the spherical gas bladders which enable them to float. So sargassum is a type of macroalgae, and they create blooms across areas of the Atlantic. So we're talking the Caribbean, the Gulf of Mexico, and the tropical Atlantic through to West Africa. Okay, so sargassum is an emerging environmental challenge, and what we mean by this is that it's a new challenge. So before 2011, there would be small amounts of sargassum that would exit the Sargasso Sea system, where it seems to originally be from, and go across the Atlantic. And so you can see on the images on the left that there's before 2011 we've got a few sort of thallus or clumps of sargassum, individual sort of bits, but from 2011 onwards we have these huge amounts of it. So you can see in the top image that it's all stacking up along the beach, and in the bottom image it looks like a giant brown carpet, but this is actually a big sargassum bloom over the ocean. So what's going to happen now is I want you guys to have a think about why you think that there's been this change. So now that you've had the think about why you think that change might have happened, I'm just going to talk you through some suggestions and potential reasons for seaweed blooms. So we have this idea of the planetary boundaries, which was developed by Rockstrom, and essentially what this is that there's lots of different biosphere tipping points, and when these are exceeded we see changes in the world. So we've got fertilizers entering the ocean system, so you can see down the bottom there we've got biochemical flows, we've got phosphorus and nitrogen, so these can act as fertilizers in the ocean and could be encouraging the blooms. We've got oceanic events, so there's been some papers such as Johns et al. In 2020 which showed that it's the North Atlantic Oscillation that triggered the first blooms in 2011 and encouraged the sargassum to move out the initial Sargasso Sea. Other things such as El Niño's Southern Oscillation, various other oceanic events. We've also got atmospheric events, so Saharan dust storms in a similar way. They can act as fertilizers. Seasonal wind patterns can cause surface aggregation, so these they might have been more individually spread, but the winds are encouraging them to group together almost. And of course we've got climate change, which could be a potential reason. So we've got warming of the ocean and changes in salinity and various other things as effects of climate change. So why do we care about sargassum? Why is it important? So sargassum has lots of environmental impacts. For example, if we consider biodiversity, it acts as a refuge for lots of small fish and crustaceans where they can hide from predators. So it can have population impacts. So where lots of smaller fish are finding more refuge, perhaps larger fish or their predators are struggling for food, and their populations might be affected because of that. If we think of turtles, we've got neonate hatchlings which struggle to climb to the beach. So they've not only got to climb through the sand, they've also got to climb through sargassum as well. So they face lots of challenges in getting to the ocean, and also they often they use sargassum as a refuge as well. And where sargassum is floating towards coastlines and towards the beach, they often think they've swam quite far enough and they feel that they're safe in these rafts, but these rafts are being beached, so they're not as safe as they think. So there's lots of biodiversity implications going on. We can talk about beach and sand dune stability. So sargassum could contribute to sand dune stability and shoreline stability, but it depends on the area and region. There are some places which claim that it's encouraging erosion. So it's an interesting thing to be discussing. But socioeconomic impacts, so if we consider tourism, for example, tourists come to the Caribbean and Mexico and places like this where they expect to see white sand, bright turquoise water, pristine beaches, but what they're faced with instead is some sargassum, or what they hear about is sargassum, and they're off put by coming to visit these places. And lots of beach activities are influenced by sargassum. For example, you can't go jet skiing because the seaweed can get tangled in the engines and things like that, so it's affecting lots of tourist businesses. On fisheries, we've got fishermen struggling. They're getting lots of the seaweed caught in their nets, having to spend longer time repairing kit, cleaning kit, things like that, and they often have to change their fishing sites, for example. So there's lots of potential negative socioeconomic impacts which we can think of, but actually sargassum could also present lots of opportunities to communities, for example, as biofuels, potentially as soil fertilizers, bioplastics. People are creating plates, construction blocks, all sorts of things out of sargassum, so it could be quite a valuable resource in the future. So just thinking about putting this in context, why is mapping useful and where does sargassum fit into this? So we've got here the disaster risk management cycle, and it's a way of managing hazards. So where we're looking at the moment is preparedness. So if we can anticipate where the sargassum is and we can map its location, we can help communities prepare to respond to these large mats coming in. So it means they can prepare cleanup crews, or they can make sure that they fish in different areas, or they fish at certain times and things like that. So we can reduce the effect of the hazard and reduce the effect on the economic impacts that are affecting communities at the moment. So just an example of a hazard map is here. For example, we've got Nevada del Ruiz, which is a volcano. And what we can see here is that we can map the lava flows, for example, and the flow hazards, and it means that we can plan. So, for example, if we look at Armero around here, you can see that there's lots of lava flow hazards. So we can plan to not build properties there, to not expand the town there, but perhaps go for alternate areas which are not affected by these hazards, and make sure that we are protecting communities. So if you've done part 1 of Introduction to Research Methods, you might have seen these next few slides already, but what we're going to do is we're going to go over them, and we're going to have a quick quiz for you. So global change, why does it matter? So to put remote sensing into context, I just want to start by thinking about global changes generally. I think one of the most notable changes is the world's growing population and the demands that has. If we think about this in the context of the environment, changes in the environment can have impacts on communities. For example, on water, we can see that an increased population has higher water demand and can impact water stress levels. And changes like these are more recently compounded by climate change. In the context of sargassum, there are socioeconomic and ecosystem impacts on the affected communities, such as fishes. So essentially, the environmental changes matter, as they have socioeconomic and environmental impacts, and knowing about them can allow us to potentially do something about it. So a quick question for you is, can you come up with a local example of an environmental change occurring in your geographic region? So thinking about what we need to be able to monitor and detect environmental changes, we need something with global reach, something that's cost effective, something that's time effective, and we also need something that will be able to tell us information, so give us data about the change. And there's some other things we might want to know. So thinking about sargassum, it might be the volume that's important and any temporal patterns. A simple solution to this could be using satellites to collect data which ticks all of these boxes. So a question for you is, can you think of any other monitoring techniques? And maybe you can think of a monitoring technique suitable for your local environmental change that we mentioned in the last question. So satellites are a type of remote sensing, which is the science of obtaining information about objects or areas from a distance. They're most commonly used as the data they collect is often freely available, and their regular orbit means that the data is continuously and regularly collected. So can you guys think of some other remote sensing platforms? So the electromagnetic spectrum is the range of frequencies of electromagnetic radiation. Frequency range is divided into separate bands, and the electromagnetic waves within each frequency band have different names. So if we begin at the low frequency end, so long wavelength end of the spectrum, these are radio waves, microwaves, infrared, visible light, then ultralight, X-rays, and then gamma rays are at the high frequency, so short wavelength end. The electromagnetic waves in each of these bands have different characteristics, such as how they are produced, how they interact with matter, and their practical applications. So thinking about this in the context of sargassum, let's have a quick think here. What do you think, which band is sargassum most distinguishable in? Near infrared, shortwave infrared, visible, microwave, or red edge? So when electromagnetic radiation interacts with the Earth's surface, it can be reflected, absorbed, or transmitted, and each object on the Earth's surface reflects, absorbs, and transmits different amounts of electromagnetic radiation, and these differences produce a unique spectral signature of each object. So if we have a look at the graph here, we can see, for example, soil being the red line, it reflects less in the visible, more in the near infrared, and even more in the shortwave infrared. So we can see that each property here, we've got water with phytoplankton, clear water, healthy vegetation, rocks, and soil all have different spectral signatures. So based on this, what do you think is a good wavelength to distinguish between soil and vegetation? So in the context of sargassum, we need to distinguish between sargassum and water. So we can see here on this graph that there's two different lines, one for algae-laden water and one for clear water. So where do you think, or which wavelength do you think is a good point to distinguish between algal water and clear water? We can use these different reflectance characteristics of different surfaces to our advantage. By manipulating the different wavelength bands, we can distinguish different features in an image. For example, NDVI allows us to measure greenness, and this calculation of near infrared minus red divided by near infrared plus red gives us a ratio where pixels in an image are placed on a scale of -1 to 1. So if we look at the image here on the left, we can see that visible red in healthy vegetation has much lower reflectance than red band in unhealthy vegetation, and then in near infrared we can see that it's slightly higher in healthy vegetation and slightly lower in unhealthy vegetation. So there's a table here which you can have a go at filling out and write if it's higher or lower, and then estimate if the NDVI will be high or low. So now that we've had a recap of remote sensing and you've had an introduction to sargassum case study, we're going to go on to looking at Google Earth Engine and JavaScript. And for this half you need to use the Sway booklet, which is a separate link available in the resources with this online workshop. The Sway booklet provides step-by-step instructions, so you can refer to this and get through the practical side of it. So for this part of the workshop, we're looking at Google Earth Engine, and we've got some specific aims for this part. So by the end of this, you should be able to create a repository and new files. You have an introductory understanding of coding and JavaScript. So you should be able to define a variable, use basic maths functions, use the map object, understand some syntax, and be able to save and run some scripts. So what exactly is JavaScript? Well, to understand JavaScript and where it came from, we have to take a few steps back. So HTML is the markup language that we use to structure and give meaning to web content. For example, we define paragraphs, headings, and data tables, or embed images and videos in the page. And CSS is a language for styling, so we use it to apply background colours, fonts, layout of content in columns and things like that. And this is how websites were before, and JavaScript was then introduced as a way of interacting with this. So it allows you to create dynamic contents and control media, animate images, have buttons, and pretty much everything else. So it's a really useful language, and more recently it's been used for data management, and in this case for Google Earth Engine. So there's sort of 4 keywords that would be useful for you to know. So the first one is variables. So variables can be viewed as containers to store data. We name them as we go in the code. So in JavaScript, the way we identify a variable is we write var, and then a space, and then you name your variable. So it can be called anything you like, but you've got to remember what it is. So I recommend making a little note as you go along on what your variables are, so you can keep track. So in this case, I've put an example of our data set and then equals. So whatever data you want to store, you put on the other side of the equals. We've got functions. So function is a block of code that can be referenced by name later on, so you don't have to keep repeating a same block. And these are shown in JavaScript with sort of curly brackets. So you can see in the example there, we've got 2 curly brackets, which you can see. And yeah, so statements are another key term. So it's just the way you tell a computer to perform any action. It's a combination of values, operators, expressions, keywords, comments, anything like that. And in JavaScript, they're all separated by semicolons. And the 4th one is an array. So arrays are a data structure consisting of a collection of elements. So you can see in the image there, we've got the green squares. So we've got 10 green squares there, and you can see that they're indexed. So the first green square is identified by the number 0. So in that green square, we might have a reflectance value of an image. We might have information in an Excel table, things like that. And the first column is identified as 0, not 1. So bear that in mind if we're dealing with arrays. In this case, if we think of it in a remote sensing context, all our images are essentially arrays with reflectance value assigned to each pixel. So the first pixel will be indexed as 0. So we have 3 different types of variables. These are our storage containers. The first type is strings, the second type is integers, and the third is arrays. So the first type, strings, we write this using speech marks. So in JavaScript you can use 1 or 2. So we've got the standard var, name of variable, equals, and then we've got our string. Our second cup is integers. These are numbers, so they don't need any speech marks, and we just write equals and the number. And our third type, arrays. So arrays are noted with square brackets. So these can be made up of strings and integers, or just strings or just integers. Now, notice that all 3 are statements, so they end in a semicolon. So hopefully you've all managed to set up your Google Earth Engine accounts, and hopefully you should be looking at something like this. So I've just pulled out some features which will be useful for you. So we've got the map object, which is quite useful, and we'll be using that to draw some polygons. We've got the zoom toggle on the left and geometry tools. And we've got saving, running the script, which you'll both be using, and the console output is useful for seeing if you've got any errors. So if you see things in red, you might have forgotten a semicolon, you might have a space, you might have missed a bracket, things like that, and the console output should tell you if there are any issues. And last, we've got the layer manager. So if you hover over the layer manager, you should be able to see all your different layers of data and outputs as we go along through the workshop. So hopefully you've now completed section 1, and before you go on to section 2, there's some information here about MODIS. So MODIS Aqua is a satellite that was launched in 2002, and it has an image resolution of 1 pixel to 1 kilometre. It revisits daily, which means it completes a full orbit every day, and we can get daily images of the same place. It was originally designed with the idea in mind to monitor the Earth's water cycle, and so things like evaporation, the water vapour, clouds, precipitation, anything water related. So we'll be using data from this satellite for this workshop. So if you can go ahead and go on to section 2, where the aim of section 2 is to create a single line of code to import MODIS Aqua images for the period of June to November 2018. So hopefully you've managed to complete section 2, and here just before you go on to section 3, there's a reminder of some of the things we've already talked about. So the aim of section 3 is to visualize the image stack in true color using the bands. So as a reminder, we have bands for different electromagnetic waves, and these are split into different colours. So for example, in visible we have red, green, blue, we have near infrared, shortwave infrared, and so on. So MODIS is split up in this way, so but they're numbered. So in MODIS Aqua, the red band is band 1, the green band is band 4, and blue is band 3, and near infrared is band 2. So if you want to go on to section 3, and we can visualize our data in true color, so we'll be using bands 1, 4 and 3 to do this. And something to bear in mind is the way images are created is that they are all made of red, green and blue pixels, which is why we have these three together. Okay, so before you guys go on to section 4, I've got some script tips for you. So remember to use a semicolon at the end of a line or variable. You can use an underscore instead of space to separate words. That's especially useful for variable names and things like that outside that aren't in speech marks, as they will be viewed as separate words. You can remember also that JavaScript is case sensitive, so if you have a capital in your variable name, remember that you'll need to, when you call that variable again, you'll need to use a capital letter then as well. Remember, for commas, dots and brackets, count that they're all there, because I'm sure you've figured out by now, but Google Earth Engine sort of tries to help you and add brackets to close whenever you open them. So make sure you don't add too many, and if there's one open, there must be one closed. If there's 5 open, there must be 5 closed. So make sure that you've got the right number. And lastly, you can use 2 forward slashes to add comments or notes into your code. So these lines won't be included when you press run, and you'll be able to read back and remember what you've done, or write any notes to yourself and things like that. So yeah. So I hope you all managed to get through the practical okay. And here's some ideas where you can go next. They're also in your booklet, so you can have a look. We don't have anything to do with these resources, but we just found some free ones and thought you might like to check them out. So I hope you've enjoyed this session on looking at mapping and how we can use mapping and remote sensing to monitor environmental change. Something to think about is that while we've done all this work and maybe we might find patterns in our work, and this can be really useful for communities, but we need to combine this with social science approaches like stakeholder analysis to be able to introduce policies to communities to aid them in adapting and managing their hazards effectively. So please go on to our next workshop and learn more about the social science side of sargassum management.
You have now completed your More Than Maps workshop. Before you go, please could I ask you to take 1 to 2 minutes to complete the survey and leave us feedback on how you found the workshop and your workshop experience. This will enable us to continue to improve the workshops for future workshop participants. Thank you for choosing a More Than Maps workshop. Well done, you completed your workshop. Don't forget, this workshop is part of a 5-part workshop series. Now, obviously you've completed 1 or more workshops already, but don't forget there are other workshops you can choose from too that will increase your skills and understanding of how researchers study the coasts and especially our changing coasts. So feel free to sign up for another workshop to learn more about how we can study climate change in the context of the coast.